Now, integration by substitution is a sort of chain rule for integration, similar to the way integration by parts is a product rule for integration. So we focus on composite functions, and the way it works is we take y equal to f of g of x scaled with g dash of x, and we'll explain why later, and say we wanted to find the area under the curve between a and b. Then this area is the integral of that function. But if we make the substitution u equal to g of x, then we end up with a simpler graph with the exact same area. So that means the integral of this graph is equal to the integral of the other. But what does all of this mean? How do we integrate with respect to u? How can we visualize integration by substitution? Well, let's start with a graph of y equal to f of g of x, and recall that we can approximate the area under the curve with rectangles, and to get the exact area we take the width of the rectangle and make it as small as possible. And if this doesn't sound familiar to you, check out our integration video linked in the description below where we explain all of this. Now we're going to focus on one thin rectangle between x and x plus delta x, where delta x is some small change in x. Now let's create a third axis, the u-axis, where u equals g of x. So for example, if g of x equals x squared, and say that when x equals 2, y equals 3, then when u equals 2 squared or 4, then y is also equal to 3. Now notice how the y coordinates are exactly the same, but x and u are different. And we can fill all the coordinates of the graph like this, giving us y equal to f of u. Now the blue area here corresponds to the transformation of the pink area, and the blue area lies in between g of x or u and u plus delta u. And remember, the y coordinates stay the same, so the height of the blue rectangle is the same as the height of the pink rectangle. Only the widths have changed. So the blue rectangle has area f of u times delta u, and if we make the blue strip's width as small as possible, then the width becomes du. Now what we also know is that du by dx is equal to the derivative of g, since u is g of x, and then multiplying by dx across gives du equal to g dash x dx, which means f of u du is equal to f of g of x, as both rectangles are the same height, times g dash of x dx. So we can see that the width of the rectangle has been scaled by g dash. Now if we add up all the extremely small rectangles, then this is the same as integrating between the respective bounds, and this is our integration by substitution formula. And naturally we can extend this formula to indefinite integrals. Now that's great, but how do we use this formula? How can we utilize integration by substitution? And the way to see this is from some examples. And the type of problems you'll use substitution for are 1. Cancellation, 2. Substitution for composite functions, and 3, the most common of all, both cancellation and substitution for composition. So let's start with the first type, cancellation. Say you wanted to find the integral of sine x times cosine x. Then let's make the substitution u equal to sine x. Then we have the integral of u cosine x dx. Now we have a u in the integral, so how can we change from integrating with respect to x to integrating with respect to u? And the way we do this is we see that du by dx is equal to cosine x, which means dx is equal to du over cosine x. And so we can just substitute in for dx. Now we see that cosine x cancels out, leaving us with the integral of u du, which is just u squared over 2 plus c. And since u equals sine x, we get sine squared x over 2 plus c, which is the answer to the integral. Let's now try the second type, substitution for composite functions. So say you wanted to find the integral of 1 over x plus 1. Then we begin by substituting u equal to x plus 1, which is the inner function. Now we know that du by dx is equal to 1. That means du is equal to dx. This gives the integral of 1 over u du, which is a classic integral with the solution ln u or ln mod u. And since u equals x plus 1, we get ln x plus 1 plus c. Now for the final, most common type, both. Say you wanted to find the integral of 2x cosine x squared. Then we begin by subbing in u equal to x squared, which is the inner function. And this gives du by dx equal to 2x. So dx is equal to du over 2x. Combining everything gives the integral of 2x cosine u du over 2x. And we see that the 2x cancels out, giving the integral of cosine u du, which is just sine u plus c. And since u equals x squared, this is sine of x squared